All right, so today we're going to talk about heat transfer. But before we get to the heat transfer notes, on the back of these notes, there are a few things I want you to add. It's not a whole lot. Remember that you are writing these notes, so you are allowed to shorten them. You don't have to include all the words, just make sure that you have the notes down. So, first, thermochemistry, we did talk about this, but all we're doing is studying heat energy. So, we have touched on this, but just as a reminder, thermochemistry is a study of heat energy. Also, as a quick review of potential and kinetic energy, we have talked about both. We talked about potential energy when we looked at potential energy diagrams of reactions, and we've talked about kinetic energy many, many times when we talked about particles, states of matter, gas laws. We've talked about it. Potential energy is stored energy, and in this case, energy is stored in chemical bonds. And then kinetic energy is energy of motion. So remember that when we're talking about the measure of kinetic energy, what we did is we're talking about the temperature, because temperature measures the movement of molecules. The more movement, the higher the temperature. The less movement, the lower the temperature. And everyone should know this, but just in case you don't, we measure temperature using a thermometer. This one you definitely need to get down if you didn't have to put down the other one, because the other one, like I said, was review. So if you knew that, as far as putting it down, that was up to you. But you do need to know conservation of energy, and specifically, is there a laser pointer? Yes. Specifically, you need to know this equation right here. Okay, so when you see this equation, so delta E of universe is equal to delta E of system plus delta E of surroundings equals 0. Delta, of course, means change in, E stands for energy. So the change in the energy of the universe, which is equal to the change of the energy of the system, plus the change of the energy of the surroundings, is always equal to 0. This represents conservation of energy. Just like conservation of mass says mass cannot be created or destroyed, this is exactly what energy says. Energy, conservation energy cannot be created or destroyed. So you might be like, well, what exactly is system, surroundings, and universe? So I have mentioned this a few times. So science textbooks, or like whenever you're looking at stuff online and you're looking at endothermic and exothermic, they tend to say something like heat is flowing from the surroundings into the system, or heat is flowing out of the system into the surroundings. And so, well, what is that? So what I did is I did just something simple. So we're talking about the melting example from yesterday's notes. So the ice cube is in the hand. The particular thing that we are focusing on, the process we're caring about, is the ice cube melting. So in this case, what you focus on, so whatever the reaction is, if you're doing a reaction in an Erlenmeyer flask, or if, like this example here, the ice cube's melting, whatever your focus is, whatever the reaction is, or whatever the process is, that is the system. And identifying something as endo or exo is based on how is heat flowing for that system. Is heat flowing into the system or out of the system? Okay. So the system is focusing on the actual reaction or process that's occurring. The surroundings is everything else outside of the system. Okay, so everything else. Okay. So in this case, our immediate surroundings, that really the only thing we care about is our hand. Okay, that's the only thing that we really care about. Okay. When we say universe, universe means our system and our surroundings. Okay, the universe includes everything. The reason why we say that energy is conserved is because if the system is losing heat, well, where is that heat going? Well, the heat's going into the hand. But of course, we know that melting is endothermic because heat always flows from hot to cold. So heat is actually flowing from the hand into the ice cube. So our hand, which is our surroundings, is losing the heat. The ice cube is gaining the heat. So the ice cube is a system. So the heat that the surroundings lost has been gained by the ice cube. So therefore, there is no actual loss or production of heat. It's just been transferred. That's what is going on with conservation of energy. Okay, so now looking at the front of your notes, so we're talking about heat transfer. There's 3 types of heat transfer you need to know. So first things first, heat always moves from hot to cold substances. So warm to cool, hot to cold, doesn't really matter. Same thing. Heat always moves from hot to cold. Now we have the convection section. So we're talking about convection. All right. So definition for convection. Heat is circulated through fluids like air or water. So heat is circulated through fluids like air or water. Heat can also be circulated through gases, but it's not usually it is like heat is also circulated through gases with convection. Okay, it is, but it's just not one of the big things that we talk about. But it's heated through its fluids, anything that's fluid. So gases or liquids. Okay, so air or water, because air is a gas. So heat circulated through fluids like air or water. It's circulated. That's the big key word, is that it is circulated. Okay. So here's an example from eighth grade math, eighth grade science when you had physical science last, if you didn't take IPC. So we have Earth's mantle. So heat from the core, which is in here, so heat from in here, creates what we call convection currents. So this is showing convection currents. Notice how red and then blue. So red is hot, so hot rises, and then it cools down when it hits the outside because, now there's air or whatever, if you want to look at it that way. So hot rises and then it cools down. That's why it's blue, and it goes back down. And then it heats up and it rises, and then it cools down, so it goes down. And then it heats up and it rises, and then it cools down and it sinks. So that is a convection current. So that convection current in the mantle is what moves the plates of Earth's crust. That's how we get plate movement. Next one is hot air balloons. So in a hot air balloon, there's a burner. So that burner is going to heat up the air. Whenever it heats up the air rises. Okay, so as the warm air rises, it's going to cool, because once it hits the outside of that balloon, it's exposed to outside air. So it's going to start cooling down. So when it cools, it's going to sink. Okay, and this is how hot air balloons work. So it repeatedly warms and cools, creating a circular motion. And that is also a convection current. So hot air rises and then it cools, and it rises and then it cools. Okay. Some other examples of convection would be during the fire. Like, you're always told that if you're in a fire, you should crawl and not walk. That's because hot air rises and the smoke therefore rises. So you don't want to be walking through it because you don't want to inhale the smoke. You want as much fresh air as possible, and that fresh air is going to be cooler, so it's going to be closer to the ground. Also, boiling water. So as water is at the bottom of the pan, it's really, really hot, and then that bubble pops to the top and it cools down. And then it rises and then it cools down. Okay. Also, ocean water is convection currents. Okay. Next one, here's just another example. So steam rising, Now we're looking at conduction. So this is the central one. So conduction. Conduction is when heat moves through an object from direct contact. So that is touching. In order for heat transfer to be considered conduction, it must be direct contact. The two objects, wherever the heat is flowing, must be in direct contact. Okay, that's touching. So one example is if you go to the beach and you're walking barefoot on the beach. Well, the beach, that's hot sand, and it feels hot to your feet. That is conduction, because your feet is touching that sand. And so since it's touching the sand is hot, your feet is hot. So that is conduction. So we got contact, and then we have another one with cooking on the stove. First of all, there's conduction here just from the stove to the pot. So the burner's touching the pot. So therefore, that's conduction as well. Then, because this pot is also connected to a handle, that heat is going to flow from the pot to that handle. So that is also conduction. It's by touching. Okay. All right, so more examples. We have the ice melting. Remember, the ice is in the hand, so it's the heat's coming directly from the hand and it's touching. If you ever need to go change a light bulb and you forget to let it cool a little bit and you touch it, it's going to be hot whenever you're ironing your clothes. Okay. This is also conduction. The butter is melting because heat is moving from the burner to the griddle, from the griddle to the butter. Okay, it's touching, so that is conduction. Then last but not least, we have radiation. So radiation is heat moving between objects that are not touching. So there's no touching involved whatsoever. And this is through what we call infrared rays. Okay, so radiation and rays. This is how heat is given off by the sun. Okay, so the sun's heat radiates to Earth and it warms everything. It warms us, it warms our air, the soil, the water. Okay, this is how we feel the heat of the sun. It's by radiation. Now, here's the thing, the sun's out in space, right? Okay, so the heat from the sun in space has got to hit Earth. Radiation, and this is a big thing, you might want to make a note of it. Radiation is the only type of heat transfer that can go through a vacuum. And a vacuum means that there's no air. Okay. Radiation is the only type of heat transfer that can travel through a vacuum. I guarantee you will see that question either on a test or an assignment. Roasting marshmallows. So even without touching the marshmallow directly to that flame, you're still going to get a roasted marshmallow because it's going to be toasted by the heat. Okay, so here's another example. Cold day, you sitting in front of the fire. You're not touching the fire, you're just sitting there. So you're feeling the radiation from that, or you're out camping. Okay. Other examples, space heaters, microwaves, that's a big one. Microwaves heat your food with radiation. It's heating up the water molecules in your food. And then, of course, the fire. So that one's also radiation. So here is just kind of a little like looky, like this is how it should somewhat look. If you would like to color, you can color, but you're not turning these notes in. You're going to hang on to these notes. All right, so now that you're done with the notes, the next thing you have to do is you have to do the practice. And once you're done with the practice, you are done for the day.